Okay, so hello everyone. My name is Igor. I am IT coordinator in a marine construction company called GT Corporation SE. It's a European company situated with a head office in Estonia. We mostly work in the Baltic Sea on service and repairs, sometimes in construction. But we have completed projects all over Europe. Myself, with my colleagues, Leonid Makutinsky, the project manager, and Alexey Osanov, survey expert, would like to present this presentation with our latest developments in using underwater scanning for marine service. So, first of all, I would like to tell a little bit about marine service in general. Why do we do them and why do we need the underwater scanning? So, our company works on 4 main directions. The life cycle management of ports. This magic term describes the life of the port from its construction till its deconstruction, its utilization, its annual service. So we do also diving, design and engineering, construction, repair and reconstruction. So the underwater scanning falls obviously to the first category, and I will describe a little bit what goes into this one. So we do technical inspection, maintenance of the ports during their construction, during their utilization. We also do quality control for the construction works. So usually when you have a project for the port, after construction you have to check how everything was built and is it durable enough. We do the maintenance of the port, and we do engineering and analytical services of any kind if the owner asks us to. So obviously to provide the services we need the marine service, and the current state of things is that underwater scanning has become an essential part of this service. Almost any survey we did the last 2 years included some kind of scanning. As you already possibly know, Teledyne provides one of the best equipment, if not the best, for underwater scanning with very precise data. The precision and the density of the point cloud is the main factor for using Teledyne equipment, so because it is the main factor in the service. So we receive all the data in this presentation, and I will cover 5 objects, 5 projects we did this year. So we received this data mostly on the Seabat T20, where we need more precision we use the T50, and sometimes we use the Blueview. So now I will divide the survey into 4 zones, primary zones, by type of data which we need to collect to provide our clients with the report. The final product of our survey is a report which includes the data requested by the client. So first of all, we have the seabed, the classical use of underwater scanning. What we need to provide for the survey is the terrain, the depth, scattered analysis, scattered objects analysis, and some anomalies which we may find on the seabed. We have the second zone, which we call underwater wall. It's usually metal sheet wall, pile wall, concrete wall, something like that. We have to analyze the quality of the material, the thickness, the holes, all the damage we can find. And the damage quite often goes to 0.5 millimeters, so a crack more than 0.5 millimeters is considered critical and can be the cause of accidents. And also for the underwater wall, we need to provide the spatial orientation of the constructive elements. So in case it is a wall, we need to prove it is vertical. In case it's some horizontal bearing structures, we need to prove their horizontality. So it's about angles and orientation in space. There is a zone which is kind of tricky because the water level area, or also called the splash zone, it is where the water and the air change places all the time during high tide and low tide, during waves, and it provides a significant challenge for the use of scanning. I will talk about this a little more later, but the data we gather here is practically the same, so it's part of the wall. And also we have the above water, the air area, where we need to provide the structural integrity, find all the damage, and also provide positioning of key objects like cranes, cisterns, and so on. So why do we use scanning? So, first of all, how we can gather data by other means. We can gather the data by manual measurements in dry conditions or using special hermetic chambers. It's kind of a chamber which is fixed on the wall, dried out, and it can be below sea water level. We have two ways of measurement. Hermetic chambers are very costly to build, and we use them mostly for repairs, not for service. And the manual measurements above water are usually quite limited because you have to actually go with something like a stick or equipment and just measure stuff. The classical way of doing the underwater stuff is using divers. We're one of the biggest companies in the number of divers in the Baltics. But we have having a lot of experience, to be honest, divers are very costly. They're very strict safety conditions, so it's very hard to provide those conditions in port repair. To be honest, we encounter a lot of human errors in this process. So the Baltic Sea water is very murky. The visibility is 0.5 meter and it's normal. With the 0.5 meter visibility, it is quite often that you miss about 10, 20, 50 centimeters. And all this data has to be checked and double checked. And the possibility of human error or deviation is quite high. So we also use the very old classical methods like photos, videos, and so on. But it is very dependent on water quality underwater and on weather conditions both underwater and in the air. And this is why the scanning can be a fast and cost-efficient alternative to these methods. So we actively already use this scanning for around 3 years. It is included in all the reports. I will go with a few objects for each of the zone to show you how we use the underwater scanning data to provide our customers with the final results, with the final report they're looking for. So this is the first object I will cover. It's part of an oil terminal. It has the terminal itself, the concrete part of the terminal on the far side, and it also has a metal sheet wall with some structures in the water. So it's quite representative because it has different constructive elements. So the area of the survey here was the surrounding water area and seabed, the foundations of the structures, and the metal sheet wall itself, which I will cover a little bit later. So we did the scan. You will possibly see some familiar picture here. The point cloud is quite dense. We had good data. We saw a lot of objects, but as you can see, the point cloud is not very representative. It is kind of a technical thing which other point cloud engineers know how to look at and what to look for. But for a person like a client, which is just an owner of a business, this is not representative at all. So to better visualize this data, we use meshing. This is the same place, the same terminal. After we use the meshing for better visual results. So if we zoom in a little bit, we can see that the point cloud was good enough and the meshing was good enough to see almost any object on the bottom. The size of the elements here is around 10-15 centimeters, the size of the rocks. We see an anomaly on the bottom side of the sheet wall, which also goes into our report. And also we can feel, so you can see that the mesh is completely without gaps, without any holes, which we usually get during our underwater scanning. So we can fill these gaps by interpolation. We had a gap right here, we filled it in and interpolated, and we got practically the same quality of rocks which we did on all other sides. So from this object, what we can say? For the data for the seabed, we actually see quite well the terrain, the depth, the anomalies. We see scattered objects, but the precision of 10 centimeters, which we usually do for the seabed, allows us only to describe the general shape. So we currently use ROVs and divers to check these objects manually. We make photos from both range and then include this as proof of the underwater scanning data. The second zone I will talk about is underwater wall. Two primary types of walls we encounter are pile fields. This is the beam project because all this structure except the head is underwater, so I thought it's better to represent it this way. It has 14 rows of piles of concrete columns which hold the pier. The second will be the metal sheet wall, which I will cover a bit later. So the survey here, the survey field here was the pile field and the slope. The state of the slope is also valuable for estimating the chance of accidents. If the slope goes into the sea, the bearing capacity of the piles decreases. So this is the underwater scan, the point cloud data which we did. As you can see, there are a lot of shades which are produced by the piles. So this is quite tricky. I will rotate this from the top views for better view. So if we look here, even though we did a double sweep, so we go front and back usually, we have large, around 3-5 meter shades from each pile, and nothing is seen after the third row. So scanning the pile wall, the pile field is quite challenging. And the main problem is that the backs of the piles, the shades, are not reachable by boat because it is covered by the head. And there is about 1 meter during low water level to go into it. So we cannot go to the rear side, and the only way to go there currently is by divers. The divers go there and get the data manually. But we can work with the slope. So we can use the same interpolation which we used in the seabed and reconstruct the slope if we have at least some data. So with a special program, I know that the precision of the reconstructed slope is around 10 centimeters, which is good enough for the slope. And we can use this data for the report. Data, though, is still insufficient for the shades of piles. I didn't get any data from the interpolation, it is just a method of processing, so I cannot find anything which is in the rear of the piles. But the slope can be meshed and can be used in beam modeling, which we also used in this project. And you can see it is quite good for analysis of the structure of the slope. So the back of the slope we did with divers. Everything that goes up to the 4th row we had to manually check. But this was quite useful for the visualization for the client. We have a new idea from the last TMTV session. So we found out that Teledyne has a very small and nimble Z-boat. And we would like to use this one to try and go down the pier in this 1 meter gap and scan the shades of the piles. So the ROV can also be used, the Seabotics ROV or whichever you use. But an open question which we have right now and are discussing with Teledyne engineers is the GPS tracking, because columns with metal structure in them shade the GPS signal. and there is a problem with GPS positioning. We use an Aplanix less than 2 centimeter precision system, and if we lose contact with during the shades of the piles, we can lose GPS tracking and lose accuracy. So this is right now an open question. I will go now to the second type of walls which we encountered, the metal sheet walls. So here I will show the mesh for the seabed right from the start, because we already discussed it. Nothing super serious, but we have the deep area to the left, and we have a steep area to the right. So we had to do here the seabed, the metal sheet pile, okay, including the verticality, the head, which we call the concrete slab, and we had to check for damage and all the stuff which I showed earlier. The seabed is okay, it works with us, but how do we measure verticality of the metal sheet wall using scanning? We rotate this picture again for the vertical view, and we can see that if I take the coordinates of the points and measure their coordinates from the verticality of the concrete head, the plane which is above water, there is a concrete head of rectangular form, I can measure the deviation of each individual pile in the sheet wall. So the resulting deviation map is very useful for finding problems, for prevention of accidents, and on this picture we can see the metal sheet wall going a little bit to the far, to the sea, and this presents a risk because the bearing capacity in this exact place is lower than the other places, and if I put some kind of heavy crane there, the boat can collapse. So for this zone, currently there is no scanner, but it is theoretically possible to measure thickness of the material. We can use low frequency pulses to determine the thickness of the metal sheet. But it is also currently under discussion. We can check structural integrity and spatial orientation, but the current underwater scanning cannot provide us obviously with 0.5 millimeter precision. So we have to check all the damage, which is around 2-3 centimeters or more with divers. The third zone is the water level area. I will take the metal sheet wall from the previous slide and we'll add the results of the laser scan. You can see a small gap between the laser scan and the underwater scan. This is due to wave zone, where you cannot actually precisely measure neither with laser nor with water currently. But the laser scan was also pretty good. It is quite a cheap scanner, so nothing too serious. I wanted to use this laser scanner to reconstruct the full height of the concrete slab, which goes into the report, and integrate it with the underwater scanning data. So we use the meshing and interpolation to close the gap between the laser and the underwater scans, and we cover up to +2 meters above water, and we get a single mesh or a single point cloud, whatever you would like, of underwater and laser scans together. In the final report, we provide gathering of data. So we take the seabed, we take the deviation, we add AutoCAD, we add the numeric measurements, we add the laser scan, and we combine all the data in one single plot. So when the customer sees this plot, he knows practically all the information he needs for informed decisions. So to sum up this zone, the thickness remains unmeasured, so we use divers, and we visually check the gap which we interpolate, the gap which is covered by waves and not scanned neither by water nor by laser. Also, there is a part which possibly most of us don't ever think about, are the structures above water. So this is the oil terminal from the first part. it is then another part of the mesh. We have some piles here which are the bases, the foundations of structures above water. We can use the laser scan in the raw view without processing, and we can see the concrete structures and the metal structures above. So this kind of picture also is great for visualization, because the client sees, okay, I see a crane, or I see my heavy boat here, and it is exactly where I want it to be, and it is safe. So this of course does not give us any information about the damage, but it can provide us geodesic positioning and object positioning. So how can we develop this area? First of all, we know that Teledyne provides 5 directions, which we talk a lot about nowadays: imaging, instruments, interconnect, seismic, vehicles. But unfortunately, during discussions, and as you see from these presentations, while Teledyne imaging is great, practically the best, it does not cover to the whole the area of marine service, because we have to use a lot of different other stuff to cover what we cannot do now with underwater scanning. So we talked a lot about such scans, maybe representing a 6th direction with focus on horizontal scans, because currently most of the imaging is focused on scanning the seabed or the front view. Also, we are working on the new standard for the Baltics for port service called RIL 236, the owner is Finland, and we want to include the whole chapter for underwater scanning as our recommendation. So I have a few more minutes. I would like to provide a scanner comparison, which we did. We use 3 scanners right now. They are kind of the most popular in Teledyne. I will show some specs from the Teledyne website. They are all open. So and describe a little bit what are they used for. So we use the Seabat T20 and T50. The difference between them is the angular resolution. And from the 2-meter distance on which we scan with the boat, the resolution of the T50 is around 1.5 centimeter, the T20 3.5. The Blueview 5000 has much higher frequency, so potentially can give much more point cloud data, but it is limited in range due to higher frequency and less energy of the pulse. We have depths of around 20 meters, and the distance of the objects can be even more. So we use Blueview mostly for precision scanning in close range, and T20 and T50 for the main scans. The best part of the Blueview is very light, and it can be mounted on small vehicles, and that is why we are thinking of the main candidate for the Z boat, while the T20 and T50 scanners are more heavy, and they require at least a small boat. After this description of projects, I can actually describe an ideal scanner, right? So what I would like to see. For service, we need something with a variable frequency, and ideally it would have to cover a high frequency range too. So we can use one scanner for close scans and for higher range scans. We work, for example, in Romania, in Constanța, with 50 meter depths in the water area. So we need to go deep. We need a resolution of 0.5 millimeter, but we understand that it's quite possibly unreachable with current technology, because the 25 times better resolution requires 25 times better resolution. So 0.5 centimeters could cover almost anything. We just have to cover the cracks by ourselves. But cracks are usually quite large in length, and we can see them manually. So, it should be light. So we need to be able to mount it on the Z-boat and include it in the water level area. So it should be able to work around sea level. As a last slide, I will describe the software. Possibly you are interested in how we do the meshing and how we do the combination. So we use the Teledyne BDS software solution for all the pre-processing of the cloud data. We use the 3D Reshaper. It's a French solution for cloud processing and meshing. And we use AutoCAD in the usual sense of way for BIM. If we had a single software solution, it would be great, but it would have to include everything from all the three solutions a little bit more. So it needs to get the data, work with hardware, merge point clouds, aerial scans, meshing, provide interpolation, cloud extraction, and so on. Should have plotting and provide BIM functionality in some way, at least integration with AutoCAD. So this is my last slide. I hope this was interesting to you. Thank you for listening. And if you would like to contact us, we are open for cooperation. We're interested in work with scientists, with researchers, with institutes. Any experience you have on any kind of scanning is interesting for us because we are looking for new ways to do our service and the scans. Thank you.
Teledyne Marine. Everywhere you look.